Okay, so last lesson, we got up to this problem, example 2. In the figure shown, so I'm just going to rub this one off. This is the figure that's shown. You've got technically a relation, not a function. This is a relation, and we can tell it's not a function. So if we want to make it a function, which over here, y squared equals to 9 times 1 minus x. If you expand the brackets there, essentially you got 9 minus 9x, and y will equal to the root of 9 minus 9x. And remember, when you square root, there's a plus or minus, which represents the top part must be the positive root of 9 minus 9x, and the bottom part must then represent the negative root of 9 minus 9x. Okay, so if you were to find the area under this curve between 0 and whatever this coordinate b is, for the root function, that's what you would do to find the area there, right? But then notice it's going to give you that section as well if you double it, okay? Now, the problem is that doing that problem could be tricky for some, especially if this problem here, it's actually doable since it's a root, but if it was something else, is there another way to solve the problem? That's what it is. So you can still do it this way. There's nothing wrong. You'll get the same answer as well. It's just that the alternative would be easier or quicker, okay? So let's first answer the question. Part A wants to find the intervals, both the x-intercept and the y-intercept. So let's start off. Let's find the y-intercept. Now, how do we find the y-intercept again? Let's go with Joe. Let x equal to 0. So we're saying x has to be 0 to find the point A. And the y value would then be based on the equation there. If x is 0, y squared is equal to 9 times 1 minus 0. And that gives me 9. And y is equal to the root of 9, which gives me y is equal to plus or minus 3. But based on the diagram, a must be which value? 3. Very good. So we know this point here must be 0, 3. So far, so good. Then we find B. Point B is clearly the x-intercept. So x-intercept occurs when y equals to 0. So here we go. We do the same thing again. Occurs when y equals 0. And 0 is equal to 0 squared is equal to 9 times 1 minus x. And we can see here that if we solve for that, that gives us, what's that? 0 equals 1 minus x. And x equals to 1. Okay, so I just divided both sides by 9 and then added x on both sides. Okay, so x equals 1. So what that tells me is the x-intercept must then be B, point B, it's 1, 0. So what we've understood so far is you have the first option, option 1. They say find the exact area of the shaded region. Now they've actually asked you to do this bit, and they've pretty much rearranged it all for you, but I'm saying, what if you didn't know that? If you didn't understand, what is that 1 minus y squared on 9? Where did it come from? Why is it delta y? Well, yes, you could have found the area by going from 0 to 1 of the root function, which is root of 9 minus 9x, delta x. Okay, that is one option. You can do it that way. What they've done is they said, well, instead of making vertical rectangles, sorry, let me do that again. Instead of doing vertical rectangles, which it's delta x, so the width of the rectangle is the change in the x. And the number of rectangles you make, the smaller it is, then the more accurate it is. Instead of going horizontally along the x-axis, which is 0 to 1, what they're saying is, well, why don't we make it the other way around? Why don't we do rectangles horizontally? And we find the area this way. So if you go that way, that means you are going to work along. The restriction will be then smallest value is 0, and you work all the way to 3. That is why they have that 0, 2, and the value of b there has to then be 3. So what you're looking for is now you're finding an integration between 0 to 3, and you want it to be the width of these rectangles to be the change in y. So rather than change in x, each one has a change of width of the y value. That's what you're doing. So it's a rectangle, but the change is the width of that rectangle. And so the smaller that value is, the more accurate it is. But to do that, if it's going to be delta y, that means the equation has to be in terms of y. We started off with y squared is equal to 9 bracket 1 minus x. So if you want it in terms of y, you have to then write it x as a subject. So here, if I expand the brackets, that becomes 9 minus 9x. And you can see, isolating to get the x by itself, I can add 9x on both sides, subtract y squared on both sides, and I get 9 minus y squared. Divide both sides by 9. So all I did was I just moved this across and I moved this across. Okay? And then divide both sides by 9, you get 1 minus y squared on 9. So this is now your x equation in terms of y. And since you're integrating with respect to y, then I can now say that. Why is this more preferred? Well, if you think about it, the integration of this is simply, what's the antiderivative of 1? And this one is, what's the antiderivative of y squared? It's much easier than working with the power of half. But both of them work. Okay, so if you're sort of reading that question and you were wondering where that 1 minus y squared on 9 comes from, that's what they did there. And so if you answer the question here, this is a bit easier. That would then be not x. Integration of 1 would give you y. Very good, because this is respect to y. So it should be y minus antiderivative of y squared on 9. Let's go, Rango. Very good. That is at the power by 1, so it's cubed, and then divided by the power, which is 3, but then 3 times 9 is 27. Very good. It's between 0 and 3. Using what we've learnt so far in the last session was definite integrals, so we sub in the upper value minus the lower value. So I'm substituting 3 into the equation first. 3 goes in, so it'll be 3 minus 3 cubed on 27. Take away. Very good. 0. Subbing 0 in now. 0. 0 cubed on 27. So this is the fundamental theorem of calculus. It's f of b. Take away f of a, where a and b are the two intervals. So a is 0 and b is 3 there. For those who weren't here last session. Okay. And the answer then becomes 3. Take away 3 cubed is 27. So 27 over 27 is 1. This is 0, so it all cancels out. You get an area of 2. Now, if you did it for the other one, you'd also should get the same answer as well. Assuming it's positive root, then you would get that 2 as well. If you did both positive and negative, then you get a total area of 4. Okay? So, you might question, well, both ways worked. Why do I need to integrate it along the y-axis? The second question, so if you flip over, that last question will show you when it is nice and appropriate for method students. Why did I say method students? Because the special students can probably use integration by parts to solve this question here. But technically, if we were to read this question here, you're looking for f of x, which is a log, and the area between it is between 3 and 7. So you would say integrate between 3 and 7. So find the area under the curve. F of x is log e of x minus 2 with respect to x. So it means I'm making rectangles along the x-axis, and I'm trying to find the area between 3 and 7. What's the problem? We don't have a rule for the integration of log. We've got the derivative rule for log, but we don't have an integration rule for log. In Spesh, you guys learnt integration by parts, so you can choose u and v. It's essentially the reverse of product rule. So what do method students do then? This is where integration by the y-axis, if you can't do rectangles this way, then what we do is then we say, well, let's do rectangles this way. Whoops. If I do rectangles this way, I will get the area under the same curve for this direction, but then I'm actually looking for this bit. So how do I get that bit? Well, notice it's a rectangle. If I got the area of the rectangle minus the green area, I will then have the area I actually want. Area of rectangle is easier to do. So area of rectangle, which I'll do it in purple. This rectangle here, you can find by length times width. So length is 7 units, this direction. Width, that's log E5. So that means the rectangle minus the integration, this is now integrating along the y-axis, so delta y, 0 to log E of 5, or ln 5, I'll write ln 5 just to make it easier. Log E of 5, and if I can rewrite this equation such that x is the subject and it's in terms of y, I can then solve. Now, it's likely I can do the, if I rearrange this equation in terms of y. Why? Because that'll be the inverse of log. And we know how to integrate an exponential, an e. Okay, whereas we don't know how to integrate a log. That's why this technique is going to work. So the rectangle, we can see this will give me 7 times log, or ln of 5. That'll be the area of the rectangle, minus the area of the green region, which is what I'm showing here, integration. What we're missing is what's the function. So I'm just going to rearrange it for you, and then I want you to work out what the answer would work out to be. Okay, so here we go. We started off with y is equal to log e of x minus 2. But we found that if we integrate it along the y-axis, it's better, so you need it in terms of y. So let's move everything across. How do you get rid of log base e? What's the inverse? Very good. Exponential e to the right, so e to the power of y on the left, and then e to the power of log e of x minus 2. Those are inverses. So e and log e will cancel out. You will then end up with e to the y on the left is equal to x minus 2. We're trying to make x the subject, so add 2 on both sides. E to the y plus 2 is now equal to x. That means here, we're trying to now integrate e to the y plus 2 with respect to y. That's doable because we do know the integral, the antiderivative of e to the y. We have a rule for that from our 2 sessions ago. Okay? I'm going to pause the video here. I'm going to give you 2 minutes to 3. So we know that I've rearranged it for you. We put it here, and then it's integrating or anti-deriving e to the y, which we know is still the same because the k value is 1. Anti-derive 2 is not 2x, it's 2y because it's respect to y. Subbing in the values, so fundamental theory calculus, sub in the upper value before you subtract the lower value. So subbing ln 5, so e to the ln 5 plus 2 times ln 5 minus, and notice I'm putting the brackets because minus, just making sure that you remember it's going to be minus and minus over there. So putting in the 0 and then putting in 0, the 0 times 2 will cancel out, but e to the 0 should be 1. Okay, so I can imagine some students putting a 0 here as well. Be careful, it's e to the 0, so it should be 1 there. So minus 1. E to the power of log base e will cancel out, so you end up with 5. And we get up to this step. Can I get a show of hands who at least got up to this step? Okay, good. And then the next step is just to make sure your negatives, not to make mistakes with negatives. So here it's minus 5 and then minus 1. But notice it's 5 minus 1, which is 4. And then negative 4. That should be then minus 4 there. Okay, so 5 minus 1 is 4. And then don't forget that negative. So that's minus 4 now. Notice this is 7 ln 5. And then you're minusing 2 ln 5. I know you can combine them, but what we realize is, how many of these ln 5s do we have? We've got 2 of them, and we've got 7 of them, so 7 minus 2 gives me a total of 5 ln 5s, and that's a minus 4. Now you can pull the 5 up, and you can write it as ln 25, 5 to the power 5, but I prefer that answer. Just looks nicer. 5 to the power of 5 is too big. Okay, so I would have kept it as 5 ln 5 minus 4. Is that what we all got? All right, fantastic. That's exercise E11E and 11F to work with definite integrals. That's what it was called.